Hello everyone. Today, we will explore some very interesting and important concepts related to MOSFET technology. Our focus will be on Moore's law, multigate MOSFETs, non-conventional MOSFET structures, technology nodes, and the International Technology Roadmap for Semiconductors, or ITRS. By the end of this session, you will not only understand these concepts but also their applications, limitations, and future trends in the semiconductor industry. Here we begin with Moore's law, introduced by Gordon Moore in 1965. He observed that the number of transistors on a chip doubled roughly every 2 years, leading to exponential growth in computing power and a steady reduction in cost per transistor. However, it's important to distinguish this from Dennard scaling, which said that as transistors got smaller, power density stayed constant, allowing performance per watt to scale efficiently. Dennard scaling broke down around 2005 because of leakage and thermal limits. So, while Moore's law is still about density, performance scaling slowed. This shift marked the beginning of the end of free performance gains just from shrinking devices. Moore's law's status and future. As we have seen, Moore's law is the foundational principle that has driven semiconductor innovation for decades. Originally, it stated that the number of transistors on a chip would double roughly every 2 years. But as we approach atomic scale dimensions, around 22 nanometers, 16 nanometers, 7 nanometers, 2 nanometers, this exponential scaling is hitting physical and economic limits. Companies like Intel, TSMC, and AMD are now shifting focus from pure transistor scaling to innovations like chiplets, 3D stacking, and heterogeneous integration. These approaches allow for modular design and better performance without relying solely on shrinking transistors. However, they come with challenges, especially in packaging and thermal management. Looking ahead, we're seeing exciting developments in quantum computing, neuromorphic chips, and silicon photonics, which could redefine what computing means in the next decade. Is Moore's law dead? There's been an active debate in the industry. NVIDIA's Jensen Huang claimed Moore's law is dead, pointing out that the cost per transistor is no longer halving with each node. On the other hand, Intel CEO, Pat Gelsinger, argues it's alive, but through innovation in devices, architectures, and packaging. The reality is somewhere in between. Yes, transistor density is still increasing, but not with the same cadence or economic efficiency as before. New tricks like EUV lithography, chiplet-based architectures, and 3D packaging are keeping scaling going, though at slower and more expensive steps. Company evidence, 2025 snapshot. Let's look at some company roadmaps as proof. TSMC has its 3 nanometers FinFET already in high-volume manufacturing, with 2 nanometers GA nanosheets expected by late 2025 and a 1.6 nanometer node in 2026. Intel is betting on ribbon FET and PowerVia with its 18 node in 2025. Samsung started producing 3 nanometers GA in 2022 and plans 2 nanometers soon. What this tells us is, yes, scaling continues, but via new device structures and huge investments. These are multi-billion-dollar efforts to keep Moore's law going. Continued scaling. As per Moore's law, we have some implications, pros and cons. So what are the implications? On the plus side, continued scaling allows breakthroughs in AI, high-performance computing, and even automotive ADAS systems. More transistors mean more features and better energy efficiency at the system level. But on the downside, each new node costs tens of billions of dollars to develop. Variability, leakage, and manufacturing limits make it harder to achieve consistent gains. Future scaling is expected to lean heavily on new architectures like gate-all-around, CFETs, and advanced packaging rather than pure lithographic scaling. Let us discuss multigate MOSFETs now. Why multigate? Now let's talk about device structures. As we scaled down planar MOSFETs, short channel effects became severe, meaning leakage currents and poor electrostatics. The solution was to introduce multigate transistors where the gate wraps around the channel, improving control. This structure suppresses leakage and enables continued scaling. So, without multigate MOSFETs, Moore's law would have stalled much earlier. Multigate MOSFETs design and performance. Now let's talk about multigate MOSFETs parameters. As seen, these are advanced transistor structures designed to overcome the limitations of traditional planar MOSFETs, especially as we scale down to nanometer nodes. By using multiple gates, like double gate, triple gate, or gate-all-around (GA), we gain better control over the channel, which reduces leakage and improves performance. For example, Intel used Tri-Gate technology in its 22 nanometers FinFETs, while Samsung and TSMC are now implementing G in their 3 nanometers nodes. The benefits are clear: improved electrostatic control and reduced short channel effects. But the trade-off is complexity in fabrication and higher costs. These transistors are ideal for low-power applications like mobile devices and IoT, and are paving the way for future innovations like nanowire-based GAA structures. FinFET milestone. Intel was the first to put FinFETs into mass production at 22 nanometers back in 2011. They called it the Tri-Gate transistor, which gave better performance and much lower power than planar devices. TSMC also leveraged FinFETs in its N7 and N5 nodes, and even at 3 nanometers they are still using FinFETs. So FinFETs dominated the industry for nearly 15 years, and they were the workhorse device enabling smartphones, cloud, and early AI hardware. Gate-all-around GAA nanosheet. The next big step is gate-all-around nanosheets. Instead of wrapping the gate on just 3 sides like in FinFET, the gate fully surrounds the channel. This provides even better electrostatics, especially at 2 nanometers and beyond. Companies are adopting it differently. Samsung already in 2022, TSMC in 2025, and Intel with Ribbon FET in 2025. The key advantage is design flexibility, since nanosheet width can be tuned to balance performance and leakage. FinFET versus GAA. Comparison. If we compare FinFETs and GAAs, GAAs provide superior gate control and hence lower subthreshold swing. They also allow better density scaling because of reduced cell height. But FinFETs are very mature, with excellent yields and lower manufacturing complexity. GAA, on the other hand, adds new steps like nanosheet release and inner spacers, making it more challenging. In short, FinFETs are reliable workhorses. GAAs are the future. Applications, pros and cons. Applications of GAA include mobile SoCs where power efficiency is critical, and high-performance computing where leakage control matters. Advantages are lower leakage, tunability, and continued density scaling. Disadvantages include cost, complexity, and reliability concerns like bias temperature instability. Looking forward, we expect forksheet FETs and CFETs to extend this even further, possibly stacking N and P devices vertically. Let us now discuss technologies beyond silicon channel and CMOS variants that are used for implementing circuits. Why non-conventional MOSFETs? Now beyond GAA, we face physical limits like the 60 MV DEC subthreshold swing in MOSFETs. That's why non-conventional transistors are being explored: tunnel FETs, CNTFETs, and 2D material FETs. These devices aim to either beat the fundamental limits of MOSFETs or exploit new materials with higher mobility and lower leakage. Non-conventional MOSFETs, innovations and challenges. Moving on to non-conventional MOSFETs challenges, these are devices that break away from traditional silicon-based designs. Examples include tunnel FETs, TFETs, FinFETs, HEMTs, and Nanowire FETs. Each offers unique advantages. TFETs, for instance, are excellent for ultra-low power applications due to their steep subthreshold slope. FinFETs, which are widely used today, offer high performance and scalability. However, these devices also face limitations. TFETs have low on-current, and nanowire FETs are difficult to fabricate. Despite these challenges, they're being used in cutting-edge applications like biomedical sensors and wearable electronics. The future may lie in hybrid devices that combine the strengths of multiple architectures, or even in spin-based transistors that use electron spin instead of charge. Tunnel FETs, TFETs. Tunnel FETs work on band-to-band tunneling rather than thermionic emission. This allows them to achieve sub-60 MV DEC slopes, meaning they can work at lower voltages and drastically cut power. The main issue is they have very low on-current, making them slow compared to CMOS. Today, they're being researched for ultra-low power IoT and always-on devices, but not yet in mainstream logic. Carbon nanotube FETs, CNTFETs. Carbon nanotubes are another exciting candidate because they allow nearly ballistic transport, which means extremely fast devices. They also have great electrostatics and can be fabricated at very small dimensions. But the problem is separating metallic from semiconducting nanotubes, achieving uniform placement, and reducing contact resistance. CNTFETs have been demonstrated in labs, including small libraries of logic gates, but mass production is still far away. 2D material FETs. Finally, 2D materials like MOS2 and WS2 offer atomic scale thickness, which makes them excellent for short channel control. IMEC and others are pushing roadmaps that show how 2D materials could extend scaling below 1 nanometer nodes. But challenges like wafer scale growth, transfer techniques, and defect control remain. Applications may include ultra-low power logic, wearables, and even integration in the back end of line. Let's us understand what's our technology nodes, ITRS and IRDS. What is a technology node today? The term technology node used to mean gate length or half pitch, but that's no longer true. Today, it's a marketing term. For example, a 5 nanometers node might actually have a gate length closer to 18 nanometers. The real way to compare nodes is by pitches, contact gate pitch, metal pitch. That's why different foundries' nodes at the same NM aren't directly comparable. The International Technology Roadmap for Semiconductors, or ITRS, was a collaborative effort sponsored by the 5 leading chip manufacturing regions in the world: Europe, Japan, Korea, Taiwan, and the United States. Their semiconductor industry associations came together with one mission: to ensure cost-effective advancements in integrated circuits. This roadmap served as a guide for both industry and academia, making sure that progress was not just about smaller transistors but about sustaining the overall health and success of the global semiconductor ecosystem. The ITRS wasn't just about transistor scaling. It produced detailed documents across more than 15 areas, covering the entire semiconductor ecosystem. This included traditional areas like test equipment, lithography, and process integration, but also emerging fields like MEMS and analog mixed signal. The roadmap also looked at yield enhancement, metrology, and even environmental health and safety aspects. Most importantly, it included research directions for emerging devices, ensuring the industry had a 10 to 15-year outlook to prepare for future technologies. Each ITRS update was designed with a 15-year time horizon. The roadmap anticipated the rise of the Internet of Things and the big data era, predicting a world of interconnected devices, sensors, and highly complex information processing needs. In other words, the roadmap didn't just think about making chips smaller, it foresaw how semiconductors would power whole new paradigms in connectivity, computing, and human-machine interaction. By 2012, the world of electronics had transformed: smartphones, wireless broadband, and the rapid expansion of IoT. The original ITRS structure was no longer sufficient to capture these shifts. So, a restructuring effort began in 2012 and concluded in 2014, leading to ITRS 2.0. This new roadmap streamlined the 17 technology working groups into 7 focus teams, reflecting the changing priorities of the industry. From 2015 onwards, ITRS 2.0 became the guiding framework. The ITRS 2.0 reorganization created 7 major focus teams. These included system and heterogeneous integration, which looked at combining chips and diverse technologies in new ways. Outside system connectivity examined how devices communicate with each other. The MOMORE team carried forward transistor scaling, while Beyond CMOS looked at revolutionary devices such as tunnel FETs or 2D materials. Factory integration ensured that manufacturing ecosystems could keep pace. Together, these focus teams gave a much more holistic view of the semiconductor future. ITRS and IRDS roadmap vision for semiconductor future. Let's explore the ITRS and IRDS roadmaps. The International Technology Roadmap for Semiconductors, ITRS, guided the industry until 2015, after which it evolved into the IEEE-led IRDS. These roadmaps provide a strategic vision for semiconductor development, focusing on areas like more than more, beyond CMOS, and heterogeneous integration. They highlight emerging technologies such as spintronics, photonics, and 3D ICs, and emphasize applications in cyber-physical systems, cloud computing, and IoT. One of the key benefits of these roadmaps is global collaboration and standardization. However, they also face limitations, especially in predicting disruptive innovations. Future updates are expected to focus more on environmental sustainability, AI-driven chip design, and reducing Scope 3 emissions across the supply chain. ITRS IRDS. Historically, the ITRS, International Technology Roadmap for Semiconductors, provided scaling targets until 2016. After that, the IEEE formed IRDS, which broadened scope beyond scaling, including advanced packaging, metrology, and new devices. IRDS also tracks emerging device types like CFETs and 2D materials, showing us what might happen over the next decade. What made the ITRS and ITRS 2.0 truly powerful was the teamwork. Global chip manufacturers, equipment vendors, universities, and research consortia all collaborated. Together, they identified critical industry challenges and encouraged innovative solutions, always with a 15-year outlook. Importantly, participation was open. Anyone from the semiconductor community could contribute, making it a shared global effort. The ITRS was not a closed-door exercise. Every year, it held public conferences for review and feedback. It also partnered with organizations to conduct webcasts and virtual conferences, expanding participation globally. This openness allowed scientists, technical experts, and industry professionals worldwide to engage and contribute, ensuring the roadmap reflected real-world needs and insights. Company roadmaps versus IRDS. If we compare companies to IRDS, TSMC is moving from N3 FinFET to N2 nanosheet in 2025, then a 16 in 2026. Intel is betting on ribbon FET and PowerVia at 18 in 2025. Samsung already has GAA in production and plans to nanometers soon. IBM has shown 2 nanometers nanosheet prototypes in research. All of these align reasonably well with IRDS, though each company brands its nodes differently. By 2017, the ITRS officially ended, but its impact continues through successor roadmapping efforts like the IRDS. It left behind a strong legacy of global collaboration, technical foresight, and collective problem-solving. The roadmap successfully anticipated major trends such as IoT and big data, and helped prepare the industry for the nanoelectronics era. Even though the roadmap itself is no longer updated, the cooperative spirit it fostered continues to shape semiconductor research and development worldwide. Advantages, disadvantages, future trends. The advantages of continuing technology scaling are clear. More performance, more energy efficiency, and continued progress for applications like AI and 5G. But disadvantages include skyrocketing costs, design complexity, and yield issues. Known limits suggest that silicon CMOS may reach around 1-2 nm gate lengths by 2030. Future directions include backside power delivery, CFETs, 2D materials, chiplets, and 3D stacking, essentially combining more with more than more. Quick comparison table. To summarize, here's a comparison of companies as of 2025. TSMC is on 3 nanometers with 2 nanometers planned for late 2025. Intel is moving to 18A with ribbon FET. Samsung already has 3 nanometers GA in production, and IBM demonstrated a 2 nanometers nanosheet prototype. So while Moore's law may be slowing, it is far from dead. It's evolving with new architectures and new materials. Technology nodes, scaling and industry landscape. Let's now look at technology nodes, the benchmarks of semiconductor progress. In 2025, we're seeing the transition from 3 nanometers to 2 nanometers nodes, with companies racing to push the limits. TSMC is leading with its 2 nanometers R&D, Intel is working on its 18A node using ribbon FET and PowerVia technologies, and Samsung has already deployed GA at 3 nanometers. But scaling isn't just about smaller transistors, it's about managing heat, cost, and yield. EUV lithography has helped, but it's not a silver bullet. These advanced nodes are crucial for high-performance applications like AI servers, smartphones, and autonomous vehicles. Looking ahead, we expect more emphasis on advanced packaging, sustainability, and node-flexible design strategies that prioritize performance over pure scaling.